In the last lecture, we introduced symbols into our language, and we showed how we could use them to intermix with numbers to create mixed expressions. And you'll recall that our big example was a symbolic differentiator that let us reason about algebraic expressions rather than just numerical ones. In this lecture, we're going to take that idea of symbols and combine them with lots of different data types to build what we call tagged data structures. To start, let's motivate why we need a tag, as well as what constitutes a tag. Suppose I want to get some help in creating a system to create and manipulate complex numbers. Remember that a complex number is a number with two parts. The standard way of representing it is in terms of a real part and an imaginary part. And we often represent such numbers as a vector, with one component representing the real part of the vector and the other component representing the imaginary part. Because we can think of a complex number as a vector, it's also convenient to think about representing it in terms of a magnitude, or length of the vector, and an angle, that is, the angle between that vector and, say, the real axis. Now, let's assume we have some data abstractions for complex numbers. That is, we have a constructor and we have some selectors that will pull the pieces out. And in fact, let's assume that the selectors are things like real and imag for the real and imaginary part, and mag and angle, as shown there, for the magnitude and angle of the vector. As we've seen before when talking about data structures and data abstractions, if we have those constructors and selectors, we can just think about writing code for manipulating complex numbers. For example, here's some code that will do that. Now, in manipulating complex numbers, I can take advantage of the fact that some things are easier to do in one representation than in another. For example, if I want to add together two complex numbers, it's easiest to think of this as just normal vector addition. That is, to get the sum of two complex numbers, I pull out their real parts using their selectors, just add those together using normal addition. I pull out their imaginary parts using the right selectors, just add those together using normal addition. And now I have a new real part and imaginary part, so I can glue them together to make a complex number. And in this case, I'm going to use a constructor that knows the inputs are in rectangular coordinates or Cartesian coordinates, and it's going to glue them together to make a new complex number. On the other hand, multiplication is actually easier to think about in terms of magnitudes and angles of things. So here, I can take the magnitude selector to get out the magnitude of the two vectors, or the two complex numbers, multiply them together using normal multiplication because these are just numbers. I can take out the angles of the two complex numbers, just add them together using normal form, and then construct a new complex number out of these pieces. And in this case, my constructor has to know that I'm providing it things in polar, or magnitude and angle form, not in rectangular, or real and imaginary form. And note again the key point about a data abstraction. I haven't yet worried about the details of how this thing is implemented. I'm simply using the constructors and selectors to get out the parts, manipulate them, and create new data structures that I can then go on and use. I can think about complex numbers just as numbers, not having to worry about the details. As we said, it's often convenient just to manipulate the data structures, using the abstraction barrier between the details and the use to separate out those two parts. But ultimately, we're going to have to make an implementation of the data structure. We're going to have to build the guts of it. So we need to think about how we would do that. Well, let's pass this task off to our friend Bert and ask Bert to actually implement a specific representation, a detailed representation for complex numbers. First of all, Bert's going to need a way of gluing things together. So he obviously should just use lists as a way of trying to represent the combinations of two parts. It's a standard thing we should do. He still has a choice, though, and Bert, being a rather square guy, decides to use rectangular components or rectangular coordinates as his basis. That is, his representation of a complex number will be a list of the real part and the imaginary part of the complex number. Note what this means. If he has handed a real and imaginary part, he can construct them by just gluing them together using list. On the other hand, if he is handed a magnitude and an angle, he'll need to convert that into real and imaginary part, doing a little bit of algebra, and then glue things together so that no matter how inputs are provided to the constructor, he always represents things in that form of a list of the real part and the imaginary part. To complete the representation, Bert just has to make sure that he implements selectors that satisfy the contract associated with complex numbers, that real and imaginary parts get out the right pieces of the data structure, and similarly for magnitude and angle. Here, part of this is very easy. Given that Bert has chosen to represent things in terms of a list of a real and imaginary part, the selectors real and imag just pull out those pieces of the list. On the other hand, to get out the magnitude of a complex number represented this way, we have to take the real and imaginary parts. Notice how we're going to use those selectors to get them out. Then do some algebraic manipulation to convert real and imaginary parts into a magnitude. This is just getting the length of the vector. And then returning that value. Similarly for angle, we have to get out the components, the real and imaginary parts, since that's how they are represented, and then do some algebra, in this case taking an ATAN, to get out the actual angle. There's Bert's implementation. Constructor and selectors does the right thing. Notice that Bert made a design choice. He made a decision as to how he was going to internally represent complex numbers as a list of the real and imaginary part. Let's suppose at the same time we also handed this task to Bert's friend Ernie and asked Ernie to build a representation for complex numbers, constructors and selectors. Ernie, as you may know, is from Canada, and hence he likes cold things, so he opts to represent things in polar form. That is, his basic representation is going to be to represent a complex number as a list of the magnitude and angle of a complex number. Similar to what Bert did then, Ernie has to do a little bit of work for the alternative form. So making a complex number from polar form just lists things together. If, on the other hand, Ernie's constructor is given a real and an imaginary part, we have to do a little bit of work to compute out what the magnitude and the angle of those two things are, and then create a list of those to get things into the form we want. And completing Ernie's task is also very similar. The magnitude and angle selectors just get out the pieces of the list because things are represented that way in his version, whereas for real and imaginary part, Ernie's going to have to do a little bit of work to take the magnitude and angle using the right selectors, compute from those what the actual real and imaginary parts are, and then returning those values. Once again, Ernie's data structure satisfies the contract between constructors and selectors. All that's changed is how he has chosen to internally represent a complex number. Okay, this sounds fine. We've got two different implementations for complex numbers, one in Cartesian or rectangular coordinates, one in polar coordinates, but both seem to satisfy the contract we'd like. What's the big deal? Well, suppose we pick up a complex number lying on the floor. In particular, suppose we pick up the following object, and we know it represents a complex number. Here's the question. What actual number does this represent? Gee, that sounds funny. It's just a complex number, right? But think about it. If this was a complex number made by Bert, what number would this represent? Well, in that case, we know that the first part of this number represents the real part. The second part of this number represents the imaginary part. So it corresponds to this vector, to this point, or this complex number represented in the Cartesian coordinate frame. On the other hand, if this was a complex number made by Ernie, then we know the first number in this list represents the magnitude, and the second number represents the angle. And in that case, it represents this complex number, or the end of this vector. So we've got a problem. Depending on who made this complex number, it actually represents a different thing. And how do we tell who made it? Well, that's kind of the problem. Given what we have here, we can't tell. Fortunately, the solution is easy. Let's create designer complex numbers. That is, let's have them autographed on the back by the designer. Or said a little less facetiously, let's put a label on the object that either says this is a rectangular or Bert-style complex number, or this is a polar or Ernie-style complex number. How do we add a label to our complex numbers? Well, just glue it on the front. Let's change our constructors. In particular, let's change our constructor that says if I'm making a complex number from rectangular form, I'll put a label up front that says, gee, here's the two pieces, the real and imaginary components, and here's the label that says it's in rectangular form. If, on the other hand, I'm going to make a complex number from polar form, that is, I'm given a magnitude and an angle, I'll again just glue those together, but put a label up front that says that's how it was made. It's in polar form. And what else do I need in this new kind of data abstraction? Well, I've got a label there, so let's have a selector that pulls off the tag, that it gets out whether it's rectangular or polar, and another selector that pulls out the contents. Notice the use of coulter here to get the remaining list of elements, that is, either the real and imaginary parts or the magnitude and angle, depending on which piece is used to represent it. Note carefully what I've done here. I've said now to create a complex number. No matter what form it comes in, I'm just going to list those two things together, but I'm simply going to label whether it's rectangular or polar. So I'm not doing any work to convert, I'm simply gluing the pieces together with the right label. To make sure my contract holds, I then have to think about how to change the selectors. And here's where I'm going to bury the work. Now I'll have a single selector called real. It's going to work with forms that are either in rectangular or polar form, doesn't matter which. And what's it going to do? The first thing it's going to do is pull off the tag. Rip the tag off of that complex number and check it to see what kind of beast is it. Notice we're using EQ to test equality, and we're using the quoted symbol rect to say this is a rectangular form so that we can compare it to the tag. If in fact this is a rectangularly constructed complex number, then we'll use the content selector to get out the contents of the context number, everything but the tag, and then we'll use the car operation just to get out the real part because we know it's represented the right way. On the other hand, if the tag says this is a polar form, again, note the use of the quote to get the symbol polar, note the use of EQ question mark to test equality of names or symbols. If the tag says this is polar, then I have to do some work. And what's the work? I use contents as a selector to get everything but the tag, that is the actual contents of the object. I get the car out, which I know represents the magnitude. I again get contents and get the catter out to get the angle. Use the cosine of that, and then do the work to do the right manipulation of the numbers to compute what the real part is. So here I have the following situation. I've just constructed complex numbers routinely, listing them together with a label. My selectors now have to do a little bit of work. They check the tag to see what kind of beast it is, and either just return the right value or compute what the right value should be by converting from polar form to rectangular form. And of course I do the same thing with the other selectors to make sure that the entire system works. Note the key point here. It's not that I'm dealing with complex numbers. That's simply a motivation. The key point is to notice how now I can use my complex number procedures, the things I wrote to manipulate complex numbers by adding them or multiplying them or doing other such things. I can use all of those procedures on any kind of complex number. That's really nice. It says no matter whether things are glued together in rectangular form, in polar form, or maybe even in some other form, my procedures will still work. The selectors do the right thing to pull out the parts. Notice again how I've made sure that the contracts hold between contractors and selectors. That's my standard message about data abstraction. And finally, notice how tags, or types, have made this possible for me. My type label now lets an object specify how it should be used. It lets us control the use of those objects, and in particular allows us to intertwine different versions of the same kind of object into a single coherent system. So this silly little example motivates then the key idea that we're going to be using today. That by putting tags on data structures, we can identify the right kinds of operations to apply to that data structure. And indeed, a very careful way of programming would always provide tags on those data structures to provide us with the flexibility we'd like. So tag data now says we have an identifying symbol attached to all non-trivial data values. That means everything except things like numbers and strings. And secondly, we're going to try and set things up so that we always check that tag, that symbol, before operating on the data. Why? Well, as we'll see, there's really two key reasons why tag data is the right way to go. The first is that it makes available to us a very powerful idea called data-directed programming. Here the idea is to write procedures that let the type of a data object direct the correct procedure to apply. Or said a different way, we're going to write procedures that look at the type of the data object and use that to determine what is this procedure that's specifically tuned to that kind of object. If you think about it, we just did that in our complex number example. We just changed things so that the selectors use the data type to direct to the right computation. Another example might be in, say, a graphics program. Suppose I want to compute the area of a figure. Rather than having to write one giant thing that does all of it, I could actually use the label on the kind of figure to tell me what's the right thing to do. If it's a triangle, compute it this way. If it's a square, compute it that way. If it's a circle, compute it that way. In all cases, getting out the area, but letting the type of the object tell me which procedure to use. This obviously leads to nice modular code that's going to be easier to deal with. The second key reason is that it gives us the ability to do what we call defensive programming. We want to be careful to make sure that we don't have unwarranted assumptions about inputs to our procedures. And in particular, we want to make sure that we can fail gracefully when a procedure unexpectedly receives incorrect types of inputs. As you saw in my last example where I created the selector for a complex number, I basically did that. I said, if it's this kind of thing, I know how to do that. If it's this kind of thing, I know how to do that. Otherwise, tell the user that he gave me something I don't know how to deal with. And of course the point is it's always better to give an error message back to the user than to try and assume that it's a particular kind of thing and end up returning garbage. The point being, of course, that you may not spot that somebody's given you back garbage till much later in the computation, and then debugging your system becomes much, much harder. So to summarize, we've introduced the idea of tagging data types. We've introduced that idea in order to enable us to build modular systems. And what we now want to do is look at how having those tags makes it much easier to build such systems. To show how to use both of these ideas, that is the idea of data-directed programming and the idea of defensive programming, we're going to spend the rest of this lecture looking at an extended example. A quick word of warning. We're going to look at a fair amount of code as we do this, but as you'll see, the code all builds on top of earlier versions of things in a nice hierarchical fashion, so you should be able to follow along without too much effort. And here's the example. Let's build a system to evaluate arithmetic expressions, similar to the ones we built last time with our symbolic differentiator. And what do I mean by that? not only do I want to be able to create expressions, using, for example, my constructors from before that make up sums, that give me out particular symbolic expressions like the one shown here, but I also want to be able to try and reduce or evaluate those expressions down to their simplest form if possible. And in the example shown here, I want to take that sum of just numbers and reduce it to the actual value of 38. Building a little system that can evaluate these expressions to reduce them to simpler forms certainly will be interesting on its own, but I want to add more to my system. In particular, I want to have my system not only simplify standard expressions, but to be able to work on ranges of numbers. For example, I may only know that the number lies between two bounds. I want my system to still be able to do computations based on that. And as the example shows, it says if I only know the number lies, say, between 3 and 7, and another number lies between, say, 1 and 3, I want to be able to still add those ranges together and know that the resulting number must lie somewhere between 4 and 10. And I want to be able to have my system work with scientific experiment numbers. That is, suppose I only know a number up until some precision. I'd still like to be able to evaluate those expressions. For example, saying 100 plus or minus 1 plus 3 plus or minus a half gives me 103 plus or minus some other range, in this case 1.5. So that's my goal. I want to build an arithmetic evaluation system, something that evaluates expressions, that tries to reduce them to simplest forms, and deals with standard expressions, ranges, and limited precision values. The basic approach we're going to take is to start with easy things first. In other words, we're going to do this little evaluation system for numbers, and then we'll worry about extending it to more complicated things like ranges and limited precision numbers. This sounds obvious, kind of like motherhood and apple pie, but in fact it's a very important characteristic of a well-designed software engineering project. It's always easier to extend a base system than to try and do the whole thing at once. And that's an important lesson to learn as you go about creating your own systems. One of the things you should watch for as we go through this exercise is to notice how, by doing it in this way, starting with base things and then generalizing, enables us to easily extend our system. Our goal, in fact, is to build our evaluator in such a way that it will both extend easily and safely. And what does that mean? Easily means that we're going to have to use data-directed programming to make things happen. Or said a little bit better, if we use data-directed programming as we construct our evaluator, remember that means we're going to put tags on things and use the tags to tell us how to dispatch off to the right procedure. If we do that, it will then be easy to add in new types of things. It's just a matter of creating the right tags for those structures, creating the representations for those structures, and then creating the dispatch into the procedure to handle that new type of object. To support safe extension is going to require that we use defensive programming. That is, that we be careful about how we design these things. We make sure we put the right error checks in the right places, and we're otherwise cautious about always using the tags to tell us how to go to the right place. So as I said, I'd like you to watch for how both of those themes intertwine here as we build our evaluator for dealing with expressions. To do this then, here's what we're going to do. We're going to first build our evaluator for dealing with simple expressions, just numbers. We're then going to look at a second version that extends this in the obvious manner, but which we will use to see that in fact it does the wrong thing. That incorrect observed behavior we're going to then use to actually fix the system, and we're going to continue to execute a series of cycles in which we extend the system, observe the behavior, and use the incorrect behaviors that we actually spot to build a new extension that does the right thing. As a consequence, we're going to walk through a series of such extensions, looking at how both data-directed programming and defensive programming enable us to actually build a system that handles a large range of different kinds of objects. So let's start with our sum expressions. First, we can build a constructor, and here it is. Notice the type, by the way, of this constructor. It's going to take in two expressions of any form and create for us a thing that has the type of a sum expression. And by that, we mean an expression that is specifically labeled as being a sum. Notice how we do it. We're going to attach the tag to the front of it, and here we're going to take advantage of the fact that plus tells us what kind of thing we have. So our constructor takes in two expressions of any form and creates a new tagged data type with the symbol plus identifying that it's a sum, as well as the other pieces glued together. Associated with this object will be a predicate to detect such objects. We have to find sums. So here's our predicate. Notice its type. It takes in something of any form and returns a Boolean telling us whether or not this is a sum. Look at the body. Notice that we first check to see that this expression is a pair. You might ask why. And the answer, of course, is in order to take the car of that expression, we have to make sure it's a pair. We want to take the car so we can check to see if the first element of this thing is the special symbol plus. In other words, is this actually a sum? So there are two key things here. First, note the defensive programming. We're checking to make sure we can use car, that it's safe to do that before we go off and find it, so we won't hit an error. And the second thing is, notice again the use of the symbol and the checking of equality of symbols in order to decide what kind of beast this thing is. And of course we'll need selectors for the data structures, so our types here will be things that take in some expressions, and we'll reduce out the expression by pulling out the right pieces. Notice, by the way, that we can assume that we've already checked the type of the object before we apply these selectors, so we can safely go ahead and get the cater and the catator of those two pieces. This is a pretty standard data abstraction. It's much like the kinds we've been building for the past several lectures. The only difference here is we're checking types, and we're assuming that we've already checked the type before we use selectors. The last thing to keep in mind is that here we're just dealing with sums. So the expressions are obviously just going to be expressions of sums, as we might expect. However, as we'll see as we go along, the type of the expression will be different in the different versions of a val, and that's one of the key themes we want to pick up on. Given this starting point, we can fairly easily implement our evaluator for reducing sums. Notice the type. It's going to take in either a number or one of these sum expressions, and what we want to get back out is a number. And how do we do it? Well, if the thing is just a number, return that number. Notice what we're doing here. In our data-directed style, we're going to first check the type of the expression. Is it a number? Just using the built-in scheme primitive for checking numbers. Having identified that type, we can then just return the value of the expression. If it's not a number, then we'll check to see is it a sum expression, using that predicate we just created. If we get one of those things, then notice what we do. We use the selectors to pull out the pieces of that expression. And I'll remind you that we're safe in applying those because we've used the predicate to check to make sure we have such a sum. Having pulled out those pieces, we'll recursively apply our evaluator to reduce those sums. This will allow us to, in fact, deal with more complicated things and reduce them down to simpler pieces. We're guaranteed that a val returns a number, if we've done it right, so we can simply then add up the results of those two things and return that new number as our overall value. And finally, notice the defense of programming. If the beast we get in is neither a number nor a sum expression, at this stage we don't know how to deal with it, so let's complain to the user and let them figure out what's the right thing to do. Notice, by the way, the nice form here. In essence, what we have is a base case, or simple primitives of numbers, or a recursive case, in which we pull out the pieces, reduce it to simpler problems, recursively apply the evaluation, and then reduce that to another answer. If we apply this procedure to a sum that includes within it both numbers and other sums, in fact it'll do the right thing. And you should be able to trace this through to realize how, given that this is a sum, it will first evaluate the first part, which is itself a number. It will evaluate the second part, which is a sum, and will recursively reduce that to 8, add it to 4, and give us back the 12 we want. So there's a little system. Takes in some expressions, reduces them to simpler forms. Now, let's see what happens as we try to extend it. Okay. Now let's try the obvious extension. Let's extend our system to deal with ranges as well. Here we'll need to build an abstract data type for a range, and to do it the dumb way, we'll do it without tags. As a consequence, our constructor for a range will take in two numbers and return one of these range objects, and we'll just do it by listing the min and max values together in that kind of structure. Given that choice for a constructor, the selectors are easy. Selectors for min and max will take in one of these range objects, a list that's been glued together, and we'll simply reduce it down to the piece that you want, either pulling out the car or the cater to get the min or max value. This just satisfies the contract by building on the contract for lists. Then building a procedure to add ranges is just a matter of doing the right thing, where that means use the selectors to get out the right pieces, add them together by applying normal addition to the numbers, and then gluing them back together. Let's look at this carefully. We're using range min to select out the parts. We know it's going to, by its type definition, give us out a number, so we're safe in applying plus to that to get a new number. Do the same thing with max. And then having two numbers, we can use the constructor, makeRange, to glue those pieces together, which will guarantee that the type of this overall addition is taking a range of 2 and a range 2 in, and producing a range 2 as output. Using this representation for ranges, we can now build our second shot at an evaluator. Notice the type we'd like for this thing. It should take in either a number, or a range, one of these range 2 things, or a sum expression, and we would like it to give back out either a number, if the thing can be reduced to that, or another range, if the thing came in the form of a range. So here's the procedure to do it, and look at its structure. This is our second evaluator, our broken one, we admit. Notice what it does. As before, it's going to check to see if this is a number, and just return that value if it is. It's also going to check using the predicate to see and the tag to see if it's a sum expression. If it is, notice what it's going to do. As before, it's going to try and recursively evaluate those two pieces using the new evaluator. And then it's going to try and be clever. And by cleverness we mean if both of the pieces are numbers, we'll just add them together to reduce down to a number. Otherwise, we'll use range add to add the two ranges together to give us back the range we want. So the idea is if we've got a sum, we're going to get the values of the pieces recursively and then glue them together using the fact that if they're numbers we want a number, otherwise we want ranges. And then the last check is if the object is neither a number nor a sum, we'll check to see if it's a pair. And if it is, we're assuming that it's a range because that was our choice we made for building ranges, and we'll just in that case return the expression because we can't simplify the range any further. And of course defensively, otherwise we'll complain with an error. Looks okay, right? Well, let's see. Well, as you've already probably guessed, no, it isn't right. And here are a couple of ways in which this system does not work properly. Look at the first example. If I try and construct a sum of a number and a range and then evaluate that, I'm going to get into trouble because in fact I haven't allowed for all possible cases, and in this case the system is going to complain. You can check through the code to see where it's going to complain, and it's basically, if you figure it out, going to complain because it's going to try and add two ranges together, and 4 obviously isn't a pair, you can't do anything with it. Notice why, by the way, the system's making this mistake. This is in large part because our code is making assumptions about how data structures are represented in the system, in particular about how we're representing ranges. We haven't dealt with all possible cases of crossovers of different types, and then this is causing us a problem because we haven't identified the data type properly. So first problem is we're missing a case. And here's the second problem. We really weren't very defensive here. Suppose we go ahead and add a limited precision data type to our system. Then eval2 will produce an answer, but a wrong one. And remember, what we really like is for the system to know it can't handle this kind of object and tell us, not give us something that we are misled into believing is actually correct. In this particular case, we've made a limited precision number using the same idea of just listing things together as we did with ranges, and now when we go ahead and add these two pieces together, we have no way of distinguishing them. It's a lot like our complex number example we started with. Unfortunately, in this case, the system can blithely go ahead and add these numbers, reduce them down, but it ends up with giving us something that's completely wrong. This should either be the range of 13 to 17, or it should be 15 plus or minus 2, depending whether we want this as a range or as a limited precision representation. But of course it gives us something that's neither and is really confusing and will cause us to be misinterpreting what this object represents. So in this case, we're not being defensive and we're going to get ourselves into trouble. So even though we're using a very simple example, it nicely highlights some of the key lessons to be learned in building computational systems. The first is the one we just observed, that we can end up calling the function on the wrong type of data. And that can come about for a variety of reasons. It could come about because we mistyped. It could come about because we had brain lock, or said a little better, we made an assumption about something that wasn't safe to make, as we just saw in our example where we ended up representing limited precision numbers and ranges, which in principle talk about the same kind of thing, but we mixed the representations together without being able to separate them by type. This kind of bug can also show up when we go about changing one part of a program and don't deal with another one that relates to it. All three of these sources can cause this kind of problem. The result, of course, is that the system's going to return stuff that's not useful. If we're lucky, it'll actually fail on something very easy and we'll be able to spot it. But that's not always the case. Sometimes the system will produce an answer that is perfectly legitimate but just wrong, and that will get passed down through the system, being processed by a number of procedures until finally something fails much later downstream, but now we're stuck trying to figure out what caused it. The cause may be much earlier in the stage and we won't be able to easily spot it. The real bad case is in which the program in fact continues to process appropriately, or I shouldn't say appropriately, continues to process and produces an answer, but one that's completely incorrect. We have no way of spotting that, and that's a real problem. Of course, the key problem here you can already see. We're being far too loose in how we use underlying data types to represent our current data structures. We're using lists to represent ranges without putting an appropriate label on them, and that's the obvious fix. To go back in and use tags to keep track of each of the data types and not rely on different underlying base representations to tell us what kind of beast we have. So let's go back and look at our sum expressions with this idea of using tagging. And in fact, they're already tagged. The first part of the expression actually tells us what kind of beast this is. So let's pull that out explicitly by restructuring our data abstraction to isolate the tag and its use. So we'll create a specific label called a sum tag, which we're going to represent as the symbol plus, but of course we could easily change that because we built in an abstraction isolating the representation of the sum tag from the name of the sum tag. Then we can change our constructor. Again, we're going to glue two pieces together in a list, and we'll put the sum tag up front. Again, notice by using the name sum tag, we've isolated out the particular choice of how we represent that tag from the use of the tag. And of course, the predicate also has to change. Now we're checking to see if the first element of this pair, assuming it is a pair, is equal to whatever the value of sum tag is. And the key point is, in this case, sum expression is not ambiguous. It's only going to return a true value for things that are made by makesum, assuming, of course, that we don't use the tag plus in some other way. Also notice how it's going to be easy to change this. If we want to use a different representation for sum tag, all we have to do is change that definition, and everything else will follow through. Okay, in this new, more disciplined way of using tags, we also have to go back and label our basic things, our primitives, our constants. So we'll create a tag for that. We'll use the symbol const to represent it, but again notice how by giving a name to that particular choice, we'll be able to also make easy changes. Now, what else do we need? Well, in this case, we're going to need a specific and explicit constructor, something that takes in a number and produces a constant expression by gluing that tag onto the front. Notice the change from my earlier version where we just use numbers directly. And as with the other things, we'll need a predicate to see if it is a constant expression. Again, notice the use of pair to make sure I can take out pieces of it. And then the checking to see whether the first element of this pair is equal to the value of constant tag. That is, to the symbol, in this case, const. And since I'm building a data structure, not only do I have to get the tag out, I'll also have to get out the value of it. So my selector now will be something that takes in a constant expression, strips off the tag, and reduces down to the actual value, or the number that's associated with it. So again, here we see a tag now at the front of this structure, a particular constructor that glues it together, and predicates and selectors, and the types associated with each of those. Great! Now we can restructure our eval system, and here's the new version. First, notice the type with this. It should take in either a constant expression or a sum expression. We haven't gotten to ranges yet. It takes in either a constant expression or a sum expression and produces out a number. Sounds good. And notice how it does it. In this case, it's got a very explicit type checker on each of the tags to decide the kind of beast. Is it a constant? Is it a sum? We're not using number here to check constant expressions. We're using the explicit tag typing. This leads to a very nice overall structure. It has a case for each kind of object about which it knows, and it has a failsafe. There's that defensive programming. This means if we give it some other thing than a sum or a number, it will tell us, rather than assuming what we gave it fits one of its particular data types. And of course, for a constant, it's easy. We just peel off the tag and return the number. That's all we want. For sum, well, we'll again pull out the pieces using the selectors, reduce those by recursively applying our evaluator, and then add them together to reduce out the number and return it. Looks nice, right? Well, in fact, it does look like it's got the right form, but we've still made a careless assumption. And notice what happens. If we construct a sum with the constant 3 and the constant 5, and we evaluate it, it's going to first deal with this as a sum. It's going to strip out the pieces, the two constants. It's going to simplify those, and then add them together. But notice what it returns. It returns a number, not an expression. And the problem is that we've made this unwarranted assumption. In particular, not all of the non-trivial values used in this code are tagged. And so we can still bomb out by trying to add a tagged thing to a non-tagged thing. Okay, we're getting closer, but we still have to fix this. Fortunately, the fix is easy. We need to change the type characteristics to return a tagged object. That is, a constant rather than a number. Or if you prefer, we need to make sure we put the tag on the number as we return it. So here is our new and improved eval. For the constant expression, it just returns the expression as before. We're guaranteed that that's labeled with the tag type. And notice the difference. Before, we stripped off the tag and returned the number. Here, we're returning the whole tagged thing, meeting our new type characteristic. For sums, notice what we do. We first pull out the pieces with using the selectors for addend and augend. We then recursively apply a val to those to reduce those to a simpler expression. Notice by our contract, they are going to return, if we've done it right, constant expressions. Not numbers, but tagged things. So we'll then select out the values using the right selector for constants, guaranteed that we now have numbers we can add them, and then we can construct back up a new tag type by gluing that constant tag on the front of this. It looks like more code, but is actually much cleaner. Again, select out the pieces, do the reduction, take that, get out the right portion, reduce that, and then create a tagged structure as the output. Notice in both cases now we're guaranteed to get a constant expression out as our output, not a number. And now this does the right thing. If we evaluate a sum of two constants, it returns the labeled number 8. That is, it's a constant with the tag in front of it and the value 8 associated with it. It's now satisfying this new type contract and in fact doing the right thing. If you look back at this code, you can see that in this version, as opposed to the previous one, every case in the procedure assumes tagged input, uses selectors to get out the contents, and constructs up a tagged output. It's meeting a contract that's much better. In principle, this is a good thing to do. It's going to lead to better behavior, but in fact it's not actually clean programming. Notice what we've done. We've actually intertwined operations on data types inside our procedure. Let's fix that. Let's pull that back outside to be a part of the data abstraction, and then allow our evaluation method to become much cleaner. In particular, let's let our thing for adding constants use the selectors to get out the parts, do the right thing, and construct a new data structure out the back end. This is the form we've seen before. This is nice and clean. It has a simple type contract, and it does the right thing of using the selectors and constructors associated with this particular data object. Having done that, our evaluator now has a much better form, and it still satisfies the same kind of type contract. Here, it uses predicates to check each type of a data object, with the fail-safe to deal with the ones we don't know how to deal with, and otherwise it simply dispatches to the right kind of procedure. There are no data construction and manipulation things intertwined within this evaluator, other than the selectors to pull out the pieces for the recursive application of eval. So a much cleaner way of doing this that still preserves the behavior we now want in terms of dispatching on type. So now we can step back and see what we've learned here. We now have a standard pattern for building one of these abstract data types with tag data. We're using a variable in the implementation to store the tag. That's going to make it very easy to change the tags without having to change any other parts of the code. We're always attaching the tag in the constructor as a part of our discipline, and then we're using predicates to check that tag. This lets us decide whether an object belongs to the data type or not, and that enables us to in fact build operations that very nicely operate in the same way. They strip off the tag, operate on the contents, and then attach the tag to guarantee that what we get back out is the kind of thing we started with. This pattern is something we want to use over and over again as we build complex structures and complex data types. And we've done a much better job of doing it in our particular version of simple evaluation of arithmetic expressions. Notice the discipline, though, associated with this. We have to use tag data everywhere in order to make sure this really works. And that includes making sure we tag up things that we return, and not just assuming we just want the value. As we've said, this is a very common pattern, and one that you're going to see many times in your career. So despite the simplicity and perhaps boringness of this little example, check it out carefully. Make sure you're comfortable with these ideas and with this disciplined approach to both safe and effective programming. Having learned how to better structure a tag data system, we can go back to where we started. Remember, our theme or our goal was to build a correct system for the simpler parts of our overall system, then use the same ideas to generalize to more complex parts. We've now done that for basic sums and numbers, so now we can move on to ranges. How do we deal with those? Well, I've already answered the question, right? Use the same ideas. And what does that mean? First, create a variable for the tag information. There it is. We'll define range tag to have the value of the symbol range, again isolating out the value of the tag from the use of the tag. We'll need a constructor, make range. We'll put those two pieces together in a list with the tag, just as we did before. Notice the type of both of these things. As before, we'll need a predicate that takes in any kind of thing and returns a Boolean value as to whether this is the right kind or not. It has exactly the same kind of form as before. And of course, we'll need selectors that take in ranges and produce out the numbers, satisfying the contract. So this is very straightforward and just mimics the structure we saw with our last version of the system. Okay, we've added ranges in terms of data structures to our system. Now, how do we extend our actual evaluator? Well, first, let's think about what we want in terms of the performance as specified by the types. This is now going to be something that either takes in a constant expression, a range expression, or a sum expression, all of which will be labeled by tags. And what we want it to produce for us is either a constant expression, if we can simplify things, or a range expression, if that's the appropriate type to use. Now, what do we know? We know that constants and ranges are things that should just pass through. We can't simplify them anymore. So in our evaluator, we'll have two dispatches for those. Check to see if it's a constant, just return the thing. Check to see if it's a range, just return a thing. In both cases, it'll give us back the right kind of beast. What about sums? Well, for sums, we have to deal with the possibility that the parts of the sum could themselves be either constants, sums, or ranges. and we're going to have to do something to try and simplify that. So as before, we'll select out the parts of the sum, evaluate them to get back the kind of thing that they reduce to, and then we have to deal with how to put them back together. If both of these values are constants, then we know we can simplify them, and we'll simply pass them on to constant add. Notice this nicely separates out the data structures from the operation. Constant add will take these two constants, strip off the tags, simplify, and then glue back on a tag to make sure that what we get back out is a tag type. If the two parts aren't in fact constants, then we have to represent this as a range. And here we have to be careful. The only really tricky part is how to deal with making sure these things are ranges. And that's where val to range comes in. This is a procedure that checks to see if its argument is a constant, in which case it converts it to the trivial range of x to x. Otherwise, it returns the argument itself, which it knows is already a range. And guaranteed to get two ranges in, then range add can do the right thing. Take those tagged ranges, strip off the tags, do the right things to add the ranges together, add a tag back on, and return that as a tagged expression. As we did earlier, we can pull this piece outside into the abstraction and simplify the evaluator. In particular, we can create a new predicate, and hence an implicit higher level kind of data structure that absorbs two simpler data structures that checks to see whether something is a value by seeing if it's either a constant or a range. And for this higher order kind of data structure, that is something that is a value, either a constant or a range, we can then have something that adds them together by doing what we just did inside of the evaluator, checking to see if both things are constants, and then using constant add on that, otherwise doing range add, making sure we convert things into the right form, namely into range. So again, val to range is something that if it gets an argument as a range, returns it, otherwise constructs a range from the constant. And here's why we want to do that. Now we can have a nice, crisp, clean version of an evaluator. First, let's check out the type. Now the evaluator is taking in a value expression, which is either a constant expression or a range expression, or it's taking in a sum expression. Remember, we kind of glued those two other expressions into this higher order structure. What it's going to return for us is a value expression as its output type. And notice what it now does. It has simply a dispatch on whether something's a value or a sum, just like before, using the tags to tell us where to go. In this case, we know with values, it's just going to return that expression. We're all set. In the case of a sum, once more, we pull out the parts using the selectors, recursively apply a val to simplify them, and then add those two things back up, guaranteeing we get a value back out. And finally, we have the failsafe at the bottom end. Again, notice the structure. We have a base case. We have a recursive case. That recursive call nicely strips the parts down and returns the right kind of beast. And perhaps most importantly, go back and compare this to our first evaluator. It's just as simple, literally. It's got the same kind of structure, but now because of the disciplined way in which we put it together, we handle a whole lot more things. This is exactly why we want data-directed programming. And let's think about the key things we've done. We've separated out the data abstraction implementation from its use. We've used the tags to tell us where to go, and we've built in a failsafe to make sure that everything does the right thing, and if not, we complain about it. Finally, notice the last thing we've done. All the way through this process, we've been using the type definitions of the objects and the procedures to help us reason about what sorts of things should go where. Once more, showing the power of the data abstraction to help us do all of this. Okay, the last piece then is to add in the limited precision numbers. And here we'll use the same general idea. We'll need a tag. We'll need a tag data structure with a constructor that builds it out. And we'll need just a new base case in our evaluator to deal with those kinds of things. And otherwise, we can just add the values of the simplified pieces, right? Well, think about this for a second, then go on to the next slide. And of course, as you've probably already figured out, it's not right. And the reason is that we've not been defensive in terms of how we do value add. Let's see why. Suppose I make a sum of the range from 4 to 6 and the limited precision number 10 plus or minus 1. And I then ask to reduce that. This gives me back something that says it's a range from 14 to 16. And of course, that's not right. The right answer should have either be the range 13 to 17 or the limited precision number 15 plus or minus 2. We got this other strange looking thing instead. Why? And the answer is we weren't really defensive. We didn't explicitly check for all types back in value add. We assumed that if something wasn't a constant, then it must be a range, and that didn't leave any room for a new data type. So now we've got to think about how to fix that. But just to say it a little more carefully, a limited expression is not a constant, so it falls into the else clause in value add. That means that the limited expression 10 plus or minus 1 passes on to val to range. And that means that it gets passed on to constant val, which simply returns the 10. It just pulls out that piece, just applying the selector to what it believes is the right thing. As a consequence, range add gets called on the value of range 4 to 6, and the range 10 to 10, because val to range takes a 10 and turns it into that simple version, and therefore we get back out the incorrect expression. And thus, to recap, we need to be defensive. We can't make assumptions that if something isn't a particular kind of thing, then it must be another kind of thing. So what we really need to do is to be sure to check tags before operating. Here's the change to value add. As before, we'll check to see if the two arguments are both constants, in which case we'll use constant add to do the right thing. Now, though, we'll then go on to check to see if the two things are both values. If they are, we can convert both of them into ranges and use range add to return the right kind of value expression. Otherwise, we'll complain, saying we don't know how to deal with either of these two kinds of things. And of course, there's a general message here. The rule of thumb should be, when checking types, use the else branch only for errors, not to catch other kinds of expressions. And if you go back and look at the earlier version of value add, you see that we didn't do that. We used the else clause to assume that if it isn't one kind of thing, then it must be another kind of thing. So what's the message? Well, actually, there are several. First, as you've hopefully seen, data-directed programming is a very useful tool. It's a great way to keep code clean, readable, and easily modifiable. It allows us to extend systems in a straightforward way while making sure that the things can be seen easily within the code and that we've guaranteed that we haven't made problems along the way. The second message is that to support data-directed programming, we really need to use types. We need to do it in a disciplined fashion, always checking the tags to make sure that it's correct to proceed before we go along. And as we saw in the last case, we're only going to use the else branch in our dispatches to handle errors, not to assume that something is of a particular type by a process of elimination. Unfortunately, many programmers don't do this. They think the loss of efficiency is not worthwhile, and they basically assume that someone else will do the check for them. As Andy Grove, the founder of Intel, says, only the paranoid survive. So it's probably important to make sure you're a paranoid programmer, because it'll really lead to better code in the long run.